All right, hello everybody. Welcome back to Math Background for Robotics. So you may notice that we have slides only, no video today. That's because I'm broadcasting from home, and so I cut out the live video feed to try and save bandwidth, make sure the audio comes through well. So we should be fine with just slides and audio for today. I'm actually broadcasting from home because I'm out sick, but I can't not teach because the show must go on, as they say. All right, so when we left off last time, we were looking at this exercise right here, the sprinkler system exercise. So we had two random variables, G for whether the grass is wet and S for whether the sprinkler is on. And we have true is the upper of the two alternatives and false is the lower or the second of the two alternatives in both cases. And here's the marginal distribution of S and the conditional distribution of G given S. And our goal was to compute the conditional distribution of S given G. So you guys were supposed to work on that towards the end of the lecture. So now would be a good time to pull up your notes, or pause me briefly and rapidly work out so that you can compare to the answer that I'm about to give. All right, so let's go ahead and take a look at the answer. So let's see. So the first thing that we can do, pretty easy to do, is to use the probability chain rule to figure out the joint distribution. So we know that P of G comma S is equal to P of S, P of G given S, right? And we know both of these things. P of S is this table here, P of G given S is that table here. And so we can just calculate the answer by broadcasting, right? So broadcasting means that we will take the larger table, so that table is 3/4, 1/4, 1/5, 4/5, and then replicate the smaller table along any of the missing dimensions, right? So here, just to keep things clear, we'll label the dimensions, right? So on this table, G is that dimension, and S is that dimension, right? So horizontally S and vertically G. By convention, if we don't label the dimensions, like on this table right here, we're going to take the first variable to be the rows and the second variable to be the columns. And if you didn't know that ahead of time, you could tell, because this is a conditional distribution, and so it's supposed to sum to 1 across G. So it sums to 1 across rows, and it does not sum to 1 across columns. All right, so now we're going to broadcast. We're going to take P of S, and so S, as you recall, is the horizontal direction here, and we'll replicate it across the direction that isn't there. So that G is not mentioned in this table, and so we'll replicate it across G. So for S, we have 1/3 there, and 2/3 there, and then 1/3 there, and 2/3 there, right? And you notice that even though this was listed vertically, right, S is the rows of is the columns of this table, right? And so this has to you match things up according to the matching dimension. And then here, right, G is the dimension that is not listed here, and so 1/3 is duplicated. 1/3, 1/3, 2/3, 2/3. All right. And if you multiply that out, right, that's equal to 1/4, 1/4, 1/12, 2/15, and 8/15. All right, and as a sanity check, you can punch those numbers into MATLAB or Python or whatever, and you will see that they add up to 1, because this is a joint distribution over G and S. Now, we want P of S given G, so here we have S on the columns and G on the rows. Here we would like S on the rows and G on the columns to match with a convention that the first variable goes on the rows and the second on the columns. So to do that, we just swap, right? So here I'll label again, G is vertical, and actually just to, we'll do it like that, right? S is horizontal to show that the ordering of S is increasing in that direction. And so we can just, to swap them, we just transpose the table, right? So that is the same table as 1/4, 2/15, 1/12, 8/15, but labeled with sorry. We would like these both to be the same, and I'll keep this convention so that I don't have to change things. Sorry about that. So so we're just swapping now, and so now S is the rows and G is the columns. And now to make this a conditional distribution, right, what we would like is for each column of this table should sum to 1, right? So if we calculate the sum of this column is 23/60, and the sum of this column is 37/60. And so what we would do then is we would just divide each element of this column by the sum and then each element of this column by the sum. And, you know, no longer are these very nice numbers, so I just went and calculated that out in MATLAB, and we get that P of S given G is equal to 0.6522, 0.3478. Here, let's move that. Move this a little bit so that we have room to complete it. 0.1351 and 0.864. Oops. 8649. All right, so that is that's the answer to the exercise from the end of class. Please, if you didn't understand that, post questions to Piazza, and we will go on with the remainder of the lecture. So I wanted to next give well, let's finish out this set of lecture notes, and then I'm going to give a longer example of how to use Bayes' rule. Actually, 2 longer examples. So, but first we'll finish out this set of lecture notes. All right. So let's see. So one of the important things, one of the important concepts in a probability distribution, something that we use a lot in machine learning, is independence. So independence, at a high level, what it means is that knowing the value of one random variable doesn't tell us anything about the value of the other. So in symbols, that means that when we condition on a value of y, the conditional distribution of x is equal to its marginal distribution. And the same thing, when we condition on a value of x, the conditional distribution of y is equal to its marginal distribution. We are using, by the way, so just to give you practice with broadcasting, here we're having broadcasting across the sides of an equality, right? So here, this is a table with 2 random variables as indices, x and y. Here's just 1, same thing, 2 and 1. And what we're doing is we're broadcasting, we're expanding this duplicating out this table to match the size of that one and claiming that corresponding elements are equal. All right. It is not necessarily easy, given a probability distribution, to figure out whether two random variables are independent, but it turns out that there is a good way to tell, and that is, here we'll make that a little bigger here. There. Now it's bigger. All right, so and it still doesn't want to show the whole equation. Sorry about that. All right, so we'll go back to the psi. Apologize for the window sizing problems. All right, here we go. Oh, so we have a question on Piazza about the example problem. Let me bring this. Oh, okay, so the question was, in the example problem, how did we go from the joint probability distribution to the conditional P of S given G? So let's expand this one back out and have a look at that again. So in general, right, so we know that P of S comma G is equal to P of S given G times P of G, right? And so what we need to do, we can actually just divide through by P of G. So we know P of S comma G over P of G is equal to P of S given G, right? And so to go from this joint to this conditional, what we need to do is divide this table by that table, right? So this table, we have it right here, right? This is the table of P of S comma G. So to get P of G, all we have to do is marginalize this table, which means summing out across values of S to get the probability. This is the marginal probability of seeing G, right? And this is the marginal probability of seeing not G. And so then we just do the division, which is what I did here, and get that conditional probability table. All right, so hopefully that's clear. All right, so here we go back to independence. So two variables, the easiest way to tell whether they're independent given an expression for the probability distribution is to look at factorizations of the joint distribution. So if we can take the joint distribution P of X comma Y and factor it into a product of terms that depend only on X and terms that depend only on Y, then that is the same as saying that X and Y are independent. It's actually, if you go through this exercise of computing the conditional distribution from this form, you can actually prove that this is equivalent to this, right? So if you take this as your definition of independence, then this would be a short theorem, or you could actually take this as your definition of independence and have these as a short theorem. So an example here, I've written out a probability distribution over X and Y. And again, from this, it's not obvious at all that these are independent, but it turns out that if we write P of X to be that and P of Y to be that, which you can figure out by marginalizing this table, and if you try taking the product of these two tables, you'll get this table. right? So in this particular example, it turns out that x and y are independent. All right. So just like there are conditional distributions, we can have conditional independence. So conditional independence is just independence in a conditional distribution. So let's say that we have three random variables, x, y, and z, and we condition on an event that z equals some value little z, right? Then we get a distribution p of x, y given z equals little z. And if x and y are independent in that conditional distribution, we say that they're conditionally independent given this event. All right. And if they're conditionally independent given all of the possible events, all of the values of the random variable, then we say that they're conditionally independent given z, meaning if you condition on z, then no matter what value z happen to take, x and y will still be independent. All right. And just to distinguish conditional independence from the other kind of independence that we just talked about, the other kind of independence is also called marginal independence, meaning in the marginal distribution. So if you marginalize out z, you'll get p of xy, and if x and y are independent in that, we say they're marginally independent. And if you condition on a value of z, then you get p of xy given that, that event, and if they're independent in that distribution, they're conditionally independent. Just like with marginal independence, conditional independence you can get by looking at factorizations. And this time, what we're going to do is we're going to factor it into a product of some terms that depend only on x and z, and some terms that depend only on y and z. So the conditioning variable can appear in both sets of terms, but x has to appear only in the left one, and y has to appear only in the right one. All right. So here's an example. If we have a distribution that we happen to know fits the following form, p of x, y, z is equal to p of x given z times p of z given y times p of y, then we can factor it. Here I've put square brackets around the two factors. And this contains only x and z, and this contains only y and z. And so we've demonstrated that x and y are conditionally independent given z. All right. And so this trick here, where we're given a symbolic representation of a probability distribution, right? This is a compressed representation. It's not a fully general distribution. And we're representing a possibly fully general distribution using this compressed form. And if we state that this distribution is equal to this one, then that means that there's a special property we can prove, namely that conditional independence holds. And that trick, being able to show conditional independence given a symbolic expression for the distribution, that turns out to be really useful because it lets you make minimal assumptions about your distribution, just the factored form that you're going to use to represent it, and then say something about what's going to be independent of what in the resulting distribution. But it's not completely general, right? Like it could happen that we're given a factored form that doesn't let us prove some particular conditional independence relation, but that conditional independence relation might still hold if we look at the exact real numbers that fill out the probability table. All right. So one last point, which is something that people sometimes get confused with, which is an ambiguity in notation. And that is that the expression P of A, you interpret in two different ways depending on whether A is a random variable or an event. If it's an event, P of A is the probability of that event, in contrast with P of not A, which is 1 minus P of A. Whereas if A is a random variable, then P of A is a probability table giving the whole distribution of that random variable. Usually when we use the notation, there's no danger of confusion. We know whether A is a random variable or an event. But for example, A could be a Boolean random variable, and then we would use A both for that random variable and for the event that it takes the value true. Right. So there could be some ambiguity. And if you're ever confused about which one we mean, please ask. All right, so that is that's that for that set of notes. I want to next go ahead and give a slightly longer example of using Bayes' rule. So I'm going to do it in pictures. Right. So what we effectively did in this sprinkler example was to use Bayes' rule, but there's sort of a very common way that we use Bayes' rule all the time, and you should become fluent in that way of using Bayes' rule, and that is Bayes' rule is the way to incorporate new evidence. So let's say that you have a distribution, right? And so I'm going to write that distribution as probability of x on that axis, and on this axis, the possible values that x can take. And so let's say that x can take values 1, 2, 3, 4, or 5, right? And their probabilities look like, this. Maybe 4 isn't very probable at all, and maybe 5 is the most probable, right? So this is a distribution, and so this I haven't given the exact values, but these values sum to 1, right? So this random variable, it could represent, let's say one of 5 topics that a document might be discussing, right? So we know that maybe maybe the 5 different values are sports, politics, finances, whatever, right? Like 5 different topics that a document could be about, and a priori, without any more information, category 5 is the most common and category 4 is the least common. All right, so now let's say we observe something about the document. So let's say, for example, that we observe that the document contains a particular word. So P of cat given x, right? So this is the frequency of the word cat, right? It's the probability that a document contains the word cat for each of those categories, right? And let's say, so we can make another graph, 1, 2, 3, 4, and 5, and here are the values of x. And on the y-axis is P of cat given x, right? And so maybe cats are fairly common in the first 3 categories, and they're not very common in the last 2 categories, right? And so here, this is not a distribution, right? So this does not sum to 1. Okay. So we started out, this is what we thought before we observed the word cat. Now we observe that the document does contain the word cat. And so what we want to do is we want to use Bayes' rule to figure out, we'll go to a new page here, P of x given cat. Right? So in other words, now given that we've observed the word cat, what are the posterior probabilities of the different classes of document? And so we know that this is equal to P of cat given x, P of x over P of cat, right? And so we're given, of these 3 terms here, we're given P of x, right? That's up here. We're given P of cat given x, and so we don't know P of cat. But what we can do is use the fact that this has to sum to 1, right? So we know that because this is a conditional distribution over x, it has to sum to 1. And so we know that if we just call this p of cat given x times p of x times some number eta, right? And we choose eta so that sum over all possible values of x, p of cat given x, p, this is a given sign here, p of x times eta, choose that so that that is equal to 1, right? Then we know that eta has to be 1 over p of cat, and we know that we've got this distribution, right? And so what we want to do is we'll take this multiplied by that, right? So that's 2 tables there, and then renormalize it so that it sums to 1. And so what's going to wind up happening, right? I've chosen it so that these are the same in high, these numbers are the same in low, and so 4 and 5, so 1, 2, 3, 4, 5, right? And so this is p of x given cat, and this is x, right? And so 4 and 5 are these numbers, they're going to get squashed down because it's lower here, and so 4 will be really low, 5 will be somewhat low, right? And then 1, 2, and 3 are going to each get inflated a bit. Maybe they'll get inflated to look like that, right? And so that's basically a use of Bayes' rule in pictures. And hopefully that's helpful in understanding sort of what the use of Bayes' rule is. Basically, this kind of use of Bayes' rule to incorporate new evidence is maybe the most common use in machine learning. It's certainly a very useful use of Bayes' rule. And I should point out, by the way, that you can keep doing this over and over, right? So if you see that the document contains cat, and then you see that the document contains dog, right? You can now start with this here, p of x given cat, as your input distribution, called your prior. Then you can have p of dog given x comma cat as your evidence. And then you can multiply those together and renormalize and get the probability of x given cat and dog. All right, so there's that example. And what I'd like to do is next go through essentially that same example, but a more real-world sized or slightly more realistic example. So here it is. So this, by the way, this page you can see it's linked from the syllabus post on Piazza, so you can download it and follow along. And so what I've done here is I have I'm setting up an example where we can use Bayes' rule over and over again to determine something interesting. And so you can follow along here, and I encourage you to take a look as well at the code and make sure you can follow along with the code as well. All right, so I've set it up so that I'm just going to read through the code. I've set it up that there are 100 values of our random variable, and we're going to actually have there are 100, let's call them, sorry, I've set it up so that there are 100, let's call them time steps. So that means that there are 100 different random variables. And each one of these random variables is going to have a value. And we're going to make a model of the world such that going to make a model of the world that has, let's call these random variables, I'm going to call these random variables xt for t equals 1 to 100. And we're going to set it up so that the whole distribution, p of x1, x2, up to x100, has a particular form. It's equal to p of x1 times p of x2 given x1 times p of x3 given x2, and so forth, right? So we just multiply in always the conditional probability of xt plus 1 given xt until we get up to p of x100 given x99. Okay. So this particular type of factorization, it's one that shows up a lot, and it's called a hidden Markov model. You don't need to know that. All you need to do is work with this particular factorization. All right. And so what I have given here, I've just made a plot of the conditional probability distribution of xt plus 1 given xt. And so here I've put xt plus 1 on the columns and xt on the rows, right? And so a light value is a high probability and a dark value is a low probability. And so the way this is set up, basically x, let's say if we're, if our from state index is 1, right? That's this top row here. Then our to state index is going to be slightly larger than 1, right? It's going to be maybe 5, it looks like here, with some noise, right? And so that just follows around. If our from state index is 20, you can, follow that down and figure out that the to state index is likely to be around, 24, 25, something like that, until the very end, where it wraps around. And if you're at a high numbered state, then probably your next state is going to be low numbered. Let's see. And to keep things simple, I'm just going to make, right, so here we had the distribution p of x1, p of x2 given x1, p of x3 given x2. So these ones, right, the p of x2 given x1, p of x3 given x2, these are all the same. And p of x1 is just going to be uniform. Excuse me. All right, so let's go onward. So now I'm going to sample a sequence of states, right, sequence of values of xt from this model. And so what I've got here is a bunch of MATLAB code that just does that. It's the result is plotted here. So here I've got, I've extended the time series out to have 300 time steps, and each one of the state indices, right? So what I've plotted is, at time 100, if you go up, you get this x, and the state index is something like, 10, 12, something like that, it looks like. And so I've just generated a sequence of states from the from this distribution that I just described, right? So So there's, let's see. So I think I wrote it down wrong. Yeah, so there's, so I wrote that there were only 100 of them, but you can see in this plot that there are 300 of them. So let's change that here, right? And then each xt is in 1 to 100. Sorry for that notational problem. All right. So now I've sampled, right? And I'm going to say now that this is all going on outside of my vision, right? So these are, the computer knows these values, but I don't, right? So pretend that you didn't see this plot, and we'll just go on from here. So what are we going to see? What we're going to see is a real number, which is basically it's going around and around in a circle, right? Sorry. The expected value of the real number, of the real vector, so it's a two-dimensional real vector, and the expected value of it is going to be cosine theta sine theta, where theta just goes around in a circle from the value of 1 to the value of 100. And we don't see it exactly. We get some noise with a given standard deviation sigma. And so you can see here what I've done is I've plotted the first 50 of these observations. And you can see that they sort of do go around in a circle. What I've done is I've connected subsequent observations with a line so that you can see what follows what. And so you can see it sort of goes around in a noisy circle. All right. So now let's say that I do see these observations, right? So behind the scenes, there are these integers, these x's, which I've been calling states, and they take values between 1 and 100, and they noisily determine the observation that I see on each time step, which is going to be a two-dimensional vector that's somewhere approximately on the rim of a circle. All right, so now what I'd like to do is use Bayes' rule to figure out what x was, right, given these observations. And so the first thing is that I can figure out the probability of each observation given particular values for the corresponding state. So you can notice up here that when we generate the observation, each observation depends on the each observation depends on the observation at time t depends on xt only, right? So that let's write that down actually because it's going to be important, right? So we'll call the observation y, and it's in yt, and it's in R2, and p of x 1 to 100 and y 1 to 100. We're going to say it's equal to p of x 1 to 100, right? Where this is of this form right there, times p of y1 given x1 times p of y2 given x2, and so forth, times p of y, again, this should be 300, sorry, 300, 300 given 299, 300, 300, 300, up to y 300 given x 300. All right, and so here, this factored form, right, is stating that yt is conditionally independent of, let's say, x1 given xt, right? So this factored form tells us something about the conditional independences in our distribution. All right, so Now, if we want to go and track everything, let's see. So we have a new question on Piazza. Let's take a look. Let's see. So somebody wants to know how to run the code. The code is in MATLAB, so you would need to have MATLAB installed. It would actually be fairly easy to translate it into another language. So, for example, if you wanted to translate it into Python, that would be a fairly a good exercise. But yeah, the code is in MATLAB, so you would need MATLAB installed to run it. Or the output of the code is shown in the notes page that I handed out. So you can follow along that way. All right, and so there's another question to explain this application scenario. Not sure exactly how to answer this, right? So I'm trying to explain an application scenario right now. So the application scenario is that we have these 300 x variables, x1 through x300. They're related by a particular probability distribution. We have these and these x variables, they take values in 1 to 100. We also have these y variables, which take values in r squared, and they're related to the x variables according to the model that I just described. And what we're trying to do is work out how to back out the probability of the x's given some observations of the y's. So if you want to imagine maybe a more concrete scenario where something like this might be true, think about your car's GPS would be a good example. So imagine your car is driving around a circular track, right? And we've discretized the circular track into 100 positions, and we observe it for 300 time steps. And each time we don't see exactly where the car is, but we see what the GPS sensor says. And so what the GPS sensor says is a noisy report of the position of the car. And so what we'd like to do is go and infer what was the actual position of the car, given the noisy report of the GPS sensor, right? So maybe that would probably be a nicer, more concrete scenario that would cause you to have this probability model. But for what I'm doing, it doesn't actually matter where the probability model comes from. We're just showing a particular way to manipulate it. So using Bayes' rule to get to figure out the probability distribution over one set of variables given observations of another. All right. So so the first thing that I can do is I can figure out P of y given x. Right? So to get what we're going to do is we're going to just keep using Bayes' rule, starting from the first time step and moving forward, right? So we have P of x1, that's just uniform, and then we have P of y1 given x1, and we can use Bayes' rule to compute P of x1 given y1, right? And so the way we do that is exactly like I showed before. First we calculate P of y1 given x1, right? And so what I've shown here is for all time steps, what is the probability of the observation we actually got given each possible state that we could have been in, right? And so, for example, at time step 100, it looks like we got an observation where states in the range of like 10 to 15 are the most likely. Right? And so this is exactly what we had before in the document example, right? We have p of y given x, and we have p of x, and we can use Bayes' rule then to get p of x given y. And the way we do that is we just component-wise multiply the two distributions and renormalize so that they sum to 1. And then we can recurse. We can do that again, right? So we can now get p of x2, right, given y1, right, given all of the observations up to the current step, but not including it, right? And the way we do that is just by using these transition probabilities that we defined up here. All right, so and then we can do the same thing, calculate the observation likelihood, which is the probability of y2 given x2, and use Bayes' rule to get the conditioning in the opposite direction, right? Use Bayes' rule to get p of x2 given y2 and all of the stuff that we conditioned on before, which is y1, right? And so that's what this code is going to do. So we start from the observation likelihoods. These are p of yt given xt. And we just do a recursive pass forward in time, right? So we start with the uniform distribution on the initial state. And then we multiply the uniform distribution by the observation likelihoods. That just gets us the observation likelihoods. And we divide by that to get a probability distribution. And then we just recursively do that forward in time. So we take the previous probability distribution, we multiply it by the transition probability matrix to get a distribution at the current time step, component-wise multiply with the current likelihoods, and renormalize to get a distribution to sum to 1. Right, and so you can see what it looks like here. After we condition on the observations, we get sort of a tighter distribution over what might have happened, right? So specifically what winds up happening is that, right, so if you look up here, right, if you ignore sort of the temporal connections between the distributions at the different time steps, you get sort of these fuzzy diagonal bars, which say that, well, we know that sort of, just from a single GPS observation, we know approximately where the car is. And then by connecting subsequent time steps, we know much more precisely where the car is, because we know sort of the car is moving forward a little bit on each time step. And so we know sort of, the GPS reading one time step ago is relevant for determining its current position as well. And so we're able to tighten up our probability distribution, right? And so that's probably as far as I want to go with this example. We can actually do the same thing going backwards from the last step as well, if we want to, but I'm not going to describe that. All right, so that is basically everything I wanted to say about probability. As always, please continue to ask questions on Piazza. And I think what I would like to do next is hand out a quiz. And so I'm handing it out fairly late in the class, so I think what I'm going to do is just quickly update the deadline, so in case anybody's not watching this exactly in real time. So I'm going to hand it out now, but then I'm going to immediately update the deadline to be an hour after the end of class instead of half an hour, to allow for people who are not working in quite real time. So just a sec while I update that deadline. All right, there we go. And all right, it should be visible to everybody now on both Canvas and Piazza. So I'm gonna pause and give you guys some time to work on it, and we'll be here to answer questions. So we'll be watching Piazza. All right, hello everybody, we're back. We don't have very much time left in the class period, but I wanted to just briefly get started on our next topic. If you have not finished the quiz, feel free to pause me and come back to this later. It looks like good fraction of people have had time to complete the quiz, so let's go ahead and get started on vector spaces. We are, for now, done with the probability topic. We'll return, of course, we'll use probability a lot later, but we're going to switch now to talking about linear algebra. And one of the most important concepts for linear algebra is a vector space. Probably you've all seen at least one example of a vector space before, which is Rn, the space of n element vectors of real numbers. You've probably spent a bunch of time manipulating these vectors in classes ranging from math to physics. And so what's important about Rn? Like what makes it convenient to work with, right? So it supports, you can think of it as a data type, right? Rn vectors, real valued vectors are a data type, and they support certain operations like addition and scalar multiplication. Given vectors, given a vector x and scalars, given a vector x, a vector y, and a scalar ax plus y is a vector. And addition is associative and commutative. You can distribute multiplication over addition, right? There's like all of these standard properties that you use to manipulate expressions involving vectors. We're going to try and abstract these properties away from just the vector space Rn, and we'll talk about how to do that in a minute. There are some more properties that Rn has that are useful. So it has an inner product, which is linear in each one of its arguments separately. It's symmetric, and the only way to get a vector with dot product 0 with itself is if that vector is the 0 vector. We can use that dot product to define a norm, right? The norm of x is the square root of the dot product of x with itself. So here what we're saying is that the only vector with 0 norm is in fact the 0 vector. And if we use that norm, then every Cauchy sequence converges. A Cauchy sequence is a sequence of vectors that keep getting closer and closer together. So the distance between xi and xi plus 1 goes to 0 as you go farther and farther forward in the sequence. And so that's a Cauchy sequence. And converges means that there's a limit of that sequence, and that limit is itself a real valued vector, right? So these are all properties that people use all the time about Rn. These properties, we're going to say make it a vector space. These first two properties here, we're going to say make it an inner product space, which is a type of vector space where you have an inner product. And this makes it what's called a complete inner product space. So there are other vector spaces besides just Rn. We would like, when we're working with these other objects, things like matrices or functions, and we'll see more, even more examples later, we would like to work with them using the same tricks that we use to make working with Rn easy. And the way we do that is by abstracting out these important properties. And the properties are the ones that I just talked about in the previous section. So before we do that, this kind of abstraction is really important in machine learning because there's a ton of machine learning algorithms that are designed to work on elements of Rn, right? So if you want to learn an element of Rn, which is often called a parameter vector, right? Like it could be the coefficients of a linear regression or the weights of a neural network. If you have an algorithm that learns a real valued vector, what we'd like to do is to take that same algorithm and generalize it to work on another class of objects, have it learn a matrix or a function or some of these other weirder classes of objects as well. And that gives us a nice, easy way to design learning algorithms for these more complicated classes of objects. And in some cases, it turns out that either the most effective or the only learning algorithm that we have is designed this way. All right, so the way we do this is by defining what's called an abstract vector space, or just a vector space for short. So an abstract vector space is a set which we'll call V. The elements of V we're going to call vectors, and we're going to have two operations called addition and scalar multiplication that work on elements of V. Right? So if x and y are vectors, meaning elements of V, and if a is a scalar, meaning a real number, then ax plus y is in V for any a, right? For any a, x, and y. And they have to satisfy the usual axioms that addition and multiplication always satisfy, like addition is commutative and associative, and scalar multiplication distributes over addition. So a couple of examples, we can turn m by n matrices into a vector space if we just add them and do scalar multiplication component-wise, right? So matrix A plus matrix B, we get a new matrix by adding together corresponding elements of A and B. Another example is the set of functions that take one real argument and return one real value. And we can, again, define addition and scalar multiplication component-wise. So, for example, if we take the function f plus 3g and evaluate it on x, the way we do that is by evaluating f at x and evaluating g at x and taking the first plus 3 times the second. All right. So those are abstract vector spaces. I should point out as well that you can have one vector space contained inside of another one. So for example, if you have all of the vectors in R3 whose last component is 0, that's a vector space. If you have all the vectors in R3, that's a vector space. The first one is contained inside the second one. And so the first one is called a subspace of the second one. All right, I think that's about all the time we have. So we'll stop here. As always, continue to ask questions on Piazza. I have office hours from now until 3:30, so feel free as well to contact me on Hangouts. As I mentioned before, I'm not at CMU today. I'm out sick, so you can't contact me at my office, but you can. But I will be watching Hangouts until 3:30. All right, I'll see you guys next time around. Thanks. Bye.